Welcome to the lecture on mathematical modeling of inclusion removal in Tundish. So, in the last lecture we discussed about the similarity considerations, and especially while doing the modeling for the inclusion removal, and even in the water modeling case, what should be the density of the inclusion that should be selected based on the other similarity criterias, and also other things taken into account, like the density of the inclusions in the steel or size of the inclusion in the steel. So, based on that you can take those. So, from there you can have the idea that when you model at that time, how you have to select those sizes properly, so that you can have a proper simulation. Now, we will today discuss about the aspects which needs to be taken into consideration when we do the mathematical modeling or numerical modeling of the inclusion removal processes in Tundish. So, as we know, we already discussed that the inclusions are basically going to be very harmful if they are coming inside out of the Tundish. So, we need to have the removal of the Tundish, but removal outside, or it should float that way, and apart from that there may be other conditions that may be put in, so that inclusions are trapped or inclusions are stuck to the walls or so. So, they are the part of the boundary conditions. Now, we will talk about the modeling issues, mathematical modeling when we talk about. So, that is normally handled using the Euler-Langrangian approach, where you have this is the discrete phase particle. So, inclusions being the particles, so they are the discrete particles. So, basically you need also to know that where these inclusions are going. So, we need to track them, and that is known as the tracking of their path. So, tracking of their trajectory. So, that is the aim basically when we do the mathematical modeling. So, as I told that this is normally a Euler-Langrangian type of approach. You have the fluid in which you are injecting the inclusion particles, and these inclusion particles are basically having. So, initially they will be given certain kind of velocity with which they will be going inside, and once they go into the fluid domain, then further they are subjected to the conditions which is prevalent in that fluid domain. So, when you are going for studying the doing the flow analysis with by taking the turbulent flow in consideration. So, you may have even either you can have the mean velocity component into consideration, or you can have even the stochastic component also, like you can have the fluctuating component also, that can its effect can be seen. So, basically what we do is that we will discuss that how that stochastic element can be incorporated to see the trajectory path and all that. So, so what we are talking that that's what we do. Normally you have a Euler-Langrangian type of approach, where the inclusions will be interacting with the fluid and fluid flow field. As we know, we are solving the Eulerian way, and this is done in the Lagrangian manner, and we have a particular geometry we make, and in that we are injecting the inclusion particles, and then we do that force balance. So, that is that equation is there, that is that needs to be solved. So, basically as we have seen that the inclusions will be also experiencing the buoyancy. So, they will be rising with the Stokes rise velocity, and in that case we are tracking them, we are wherever they are going. So, we try to have their motion, and we see that how they are being trapped or so. So, keeping so what we do is normally we make the geometry, we we provide the boundary conditions, and you have the normal governing equations, like initially for the Eulerian phase you have the governing equation, like you have the continuity equation, you have the Navier-Stokes equation, and you can have the equations for the turbulent kinetic energy and the rate of dissipation of turbulent kinetic energy, that is K and epsilon, if you are using the standard K epsilon model. So, in that case you are solving that, and then you are injecting the inclusion also, and so in this case you are going to solve the extra equation, that is that will be your the force balance particle force balance equation in this case. So, in the normal way we will be creating the geometry, we will be having all these conditions, and apart from that you need to solve the extra equation, and that equation will be your particle force balance, and that will be based on the force which is acting on the particle. So, if suppose we are taking for the x direction, so in the x direction Cartesian coordinate we have these equation that needs to be solved, will be dup by dt. So, that will be that is a standard equation which is even used by the even commercial courts. So, FD will be FD into u minus up, and then you will have the Gx, and then you have rho p minus rho, and divided by rho p, and then you have the source term, that is Fx. So, basically we solve this equation, and in this case this Fd into u minus up. So, this is basically the drag force per unit mass. So, this is that quantity Fd into u minus up, and you have the Fx. So, this so now this Fd basically will be in terms of the Reynolds number and the CD, its coefficient. So, normally this Fd into u minus up. So, this is known as the drag force per unit mass. And that is defined as 18 mu by rho p dp square, and then you have CD Re divided by 24. Now, the CD, so in this case rho is the density of the particle, d is the diameter of the particle dp, and your Re is the Reynolds number. So, you know that Reynolds number, based on that this value will be taken, and if you so you can have the value of this Reynolds number as rho into dp into up minus u and divided by mu. So, that will be your Reynolds number in this case, and though the CD, this is the drag coefficient. So, its value also so it can be taken, it will be basically a function of the Reynolds number, and so you may have different values. So, people can take these different values, and that will be a function of Reynolds number. So, some people may take it like A1 plus A2 by Re plus A3 by Re square. So, you will have these A1, A2 and A3, they are the constants that are for the smooth spherical particles, and they are also expressed in terms of another parameter like that will be phi. So, that phi again will be depending upon the surface area of the spherical particle taken into account. So, so you may have the different of these values. So, this thing can be taken and that can be incorporated into your model, and you can have this being solved. You can also have for the submicron particles, you have the Stokes law, that is drag law is applicable, and for those submicron particles you have this Fd as 18 mu upon dp square rho p into Ce. So, that again you have different kind of expressions you may have. So, that you can take from the respective literatures, and you can use them depending upon the different type of particles, and further that can be incorporated. So, so once you do that, then also comes that how to take the stochastic component into picture. So, apart from that before going for that you can consider all other kind of also forces, lift forces or so that may be considered for the force which is acting on the particle. What is seen in the case of the inclusion modeling in most of the codes is the use of the stochastic element, and that will be that will be known as the stochastic particle tracking, especially in the case of turbulent flow. So, as you know that in the turbulent flow you have in the flow component you will have one is the one is the fluctuating component. So, so that part needs to be incorporated on the for the effect to be seen on the particle, and that will basically be taken from the flow value. So, when you are having the flow field, the Eulerian flow field, in that case you will have the values of the turbulent kinetic energy, and from that value you can have the calculation of the fluctuating component part, and then its effect so that will be affecting the particle trajectory in that case. So, you can see that if you take that random component, and if you do not take the random component, there will be visible difference which is observed when the modeling is carried out. So, in the case of the stochastic particle tracking, so you will have the trajectory tracking that is required in the case of the turbulent flow especially, and as we know that in the case of turbulent flow your instantaneous value that will be so value will be the mean average, and then you have this is the fluctuating part. So, for knowing the effect of this turbulence, so you try to have the value of this being calculated from the turbulent kinetic energy part, and then its its net effect is seen when we draw the trajectories. So, what we do is normally when we get the value of up, So, then what we do is when we have seen the first equation, that is your this equation. So, that is integrated, and we find the value of the velocity of the particle, and then with the help of that we can have the trajectory estimation. So, that can be that we can have by having the solution of the equation, that is dx by dt equal to u p. So, you can, so once you integrate it, so you will get the value of x. So, then you understand the what is the where is that x. So, that is how you try to have the tracking of the path of the inclusions. So, so what happens that you may have the approaches by which you solve. So, you will have the trajectory equation that can be even simplified, and if you linearize these source terms and all that. So, what you see, the trajectory equation which we have written earlier, dup by dt. So, basically it is a function of u minus up, and that is it is written as 1 by tau rho, and this will be basically u minus up. So, this tau we can call it as. Now, this is basically, so that is for particle tau p, and this tau p is basically that is known as the particle relaxation time. So, it is nothing but this unit of time, and then you can solve it. So, it will be you can use these differencing schemes and discretization schemes, and then you can have the solution like up at n plus 1 time step minus up n, and that will be delta t. So, that will be dup by dt. So, it will be 1 by tau of again you have u star minus up n plus 1. So, that way it will be going. So, so that way this is being solved, and your u star will be nothing but the average of un and un plus 1. So, so that way you have and then you have again un plus 1 will be for the that will be again expressed in terms of un, and and a grad of the un part. So, that way this is the normal way of solving the equations. So, you can solve it, and your ultimate aim is to have the position. So, I mean you must know that how this x value is calculated once you know that up. So, that is by integration of this equation. Now, there are also considerations for the size distribution. So, what should be that particle size? So, there has been mention about different type of distribution of these sizes, and one of the distribution which is being used by some of the codes are the Rosen-Ramler type of distribution, and other kind of distributions also are there. So, that can be taken, which talks about the percentage of fraction of the particle mass which will be of certain size if you take certain size into this. So, that particle distribution that also can be taken into account. Now, as I was telling you that when we talk about these stochastic models. So, normally what we do is you find these u prime, or you find this v prime or w prime. So, that so they are u prime square bar, and that is under root. So, that will be expressed in terms of the kinetic energy, that will be under root 2 k by 3. So, from that k value which is there in the flow field, you try to have this u prime or v prime or w prime, that will be so that particle will be subjected to this, and then accordingly their movement will be controlled. So, that for that you will be again solving those velocity equations. you must know also the different kind of boundary conditions. So, what we saw that we have the governing equations, you have also the boundary conditions. So, you have different type of boundary conditions also there are on these discrete phases which we use. So, you will have the boundary condition for trapping, or you may have the reflection boundary condition. So, once they you may have the depending upon the elastic or inelastic collision, they will be reflected. So, that conditions may be given, like they may escape through the boundaries, or they may trap at the wall. So, all these conditions may be incorporated as the boundary conditions, and then we try to solve the equation, and we get the results. So, we try to see that how these work are done. I mean, we can see one work which is done by the group which worked with us. So, we and that is also a published work. So, in that how we make the geometry. So, in the geometry you have inlet, you have a symmetry plane. So, it is basically a 6 strand Tundish, and we also have used these flow modifiers, and this is the near, middle and far outlet from the inlet. So, that is why we have named it like that, and this is the symmetry boundary condition, and this is the inlet through which the inclusions are also inserted or allowed. And we have tried to have the use of these dams. So, we have given the different kind of nomenclature or the case name when we have put the dam height like 300, 250 and 200. So, that will be PS 01, so 203 like that. So, you have the different position 1, 2 and 3. So, that way your different height of dam at different positions have been used, and you have different names for that. So, that is simply creating the geometry. So, what I was telling, that when you use these stochastic particle tracking, in that case what has been seen was that when we did not use without the stochastic particle tracking method, that it was seen that the particle has come and it has hit the bottom wall, and then it went to the top surface, where the condition is that it will go and it will get stuck. So, that way that condition because of that it has stuck there. Now, if you go to the other condition where we have used the stochastic particle tracking, in that case what is seen is that the particle has come and then it has moved to the different places inside. So, it has a large movement inside, and then it is getting trapped, and that is what actually happens. In practical cases, this is more like that is what is telling that it will be coming, and because of that the implementation of that stochastic algorithm that will be moving inside for longer duration, and then it will have the chances to get floated. In this case if it is on the bottom, in that case it may have the chance to go through the outlets. So, that is normally lesser in this case. So, top surface is slag layer, and we have kept. So, once we use these the flow modifiers, how these transact this with and without, how these trajectories can, the inclusion trajectory can be plotted. So, that is one example. So, once you will do, you will have your own geometry, and you can use these algorithm to have the trajectory of the inclusion. Then these are some of the results. So, if you do with the different sizes of the inclusion particle, in that case you will be having certain kind of graph for the bare Tundish, and you see that you have the fraction of clusters that is removed that will normally be very high in the case of the near outlets when you are not using the flow modifiers in those cases, and then lesser than that will be the the middle outlet, and then you will have the far outlet. So, that is the inclusion removal that will be there from the Tundish. Now, there has been different other parametric studies like you do with the the studies for the different sizes, and what has been seen that if you increase the size, removal will be higher. So, in those cases you will have the larger fraction of the inclusions getting removed. So, this basically tells that if you do that, if you change the operating parameters, if you change those variables, you are going to have the different kind of results, and that you need to be you need to interpret that as per the configurations of the Tundish, as per the operating conditions of the Tundish, and in normal case, in normal water modeling, you can have those results also. You can see that how many have come through each of the outlets, and based on that you can have also the calculation of their residence times, and where they are getting stuck, or where they are getting removed. So, apart from that, you can have the many parameters being studied. Maybe you can take the different sizes, that is what has been taken. You can have different densities. Even the work has been done with the different inclusion density, and their effect also can be seen, that what is the removal rate when you take the different density, lower or higher value. So, these are normally, this is how you have to do the modeling studies on the inclusions inside the Tundish. So, we will have a few case studies also study in our final lectures in the coming time. Thank you very much.